We get ready.
Yeah, making last minute changes last night. So
Yes. Okay, good morning and good afternoon to the European colleague and good evening to our Asian colleagues. And welcome you to this World River and Delta System Source to Think webinar series. This is our Source to Think 2021 number 3, S2S21-03. So today we invite Professor Michael Steckler from Lamont Research, Lamont Columbia University, to give a talk about the Ganges-Brahmaputra Delta. So before I introduce Michael, I will say next week we have 2 more talks as always, and one talk from Wittot, and he will talk about the high latitude. This is something we really need. We talk about tropical river. Now we talk about high latitude flux and accumulation rate, sediment, organic carbon. I thought Tom Bionti here, you should be and your group should be very interested in this topic. And also we have Charlie Paul from California in 6 a.m. California time. He will talk about the Monterey Bay Canyon. That's the other great talk we are looking forward to. So this is Charlie talk. As you can see, a very beautiful map and observation data. So this next Friday, Charlie post data. And also, as I mentioned, next Wednesday, we have a talk about the high latitude, the glacial dominated void. And so 2 great talks, don't miss it. Please mark your calendar. So Michael is in now, as we said, is Lamont Columbia University research professor there. And Michael graduated 1976 from MIT, and then get a PhD, a master and a PhD in Columbia University, and a postdoc at University of Cambridge. And he's a fantastic experience working all the way, as you can see, until now. But I want to just mention about his research. His research interest mainly is sedimentary basin formation and development, sea level change, and the preservation. And so even stratigraphic record of the global change of continental margins, natural hazard, sea level, and coastal subsidence. He's focused on a lot of the in the last 20 years. As he told me in a couple minutes ago, he met Steve Goodbread in Dhaka 20 years ago. He working on the Bangladesh more than 20 years. So today he will present us the best of his research. Come out about the the ups and the downs of the Ganges-Brahmaputra based on the field observation. So we really looking forward to that. So Michael, now you can share your screen and put the presentation mode.
okay. Okay.
Yeah.
That everybody see my screen?
Yes.
Okay. So, as you said, I've been working in Bangladesh for over 20 years with a large number of people, and I'll show who some of them, talk about who some of those are as I go through, but you can see the list of universities there. And of course, as a result, I have way more material than I could possibly fit into a single talk. And so, like with Steve, it'll be just some pieces, some highlights, and also things that I've been working on recently that's relevant to this group. So, and to start, I'm going to go way back in time to sort of get the setting for the region. So if you go way back to the time of Pangaea, India was attached to Australia and Antarctica, and rifted off about well in the early Cretaceous, it drifted off, and that red circle shows where Bangladesh will eventually be. And then, as you know, India moved really rapidly to collide with Asia and deform it. You can see some of the faults and strain rate showing how most of East and Southeast Asia is being pushed out of the way by India acting as an indenter block with the famous Tapine and Monar models of that. But what that means as it goes in is that the edge of that continental margin actually runs along runs through Bangladesh, so that in fact, here you can see the edge of the Indian continent, and that actually just continues and then takes a bend by the Shillong Plateau, so that to the northwest of that is Indian Craton, and to the southeast of that is basically either very thin continental crust or oceanic crust, perhaps heavily intruded and covered by very thick sediments. So, this is essentially off the coast, so that in the Eocene, this was actually the location of the shelf edge. And so all the sediments coming down the Himalayas and Brahmaputra have built this entire delta, and the shelf edge has advanced on the order of 300 to 400 kilometers seaward. Okay, and in addition, besides India's going up, and Bangladesh is really along the flank of that Indian plate. So the Himalayas taking the full brunt, but along the side you can see it's a lot of strike slip motion. It's very oblique. So India is moving a little bit to the northeast, so there's some convergence, and so you have the subduction zone coming in and then hitting the delta. And here you can see the contours of the slab from slab 2.0 and a zoom up of our area. And one of the things you can see the slab, and these are the subduction volcanoes in Myanmar. There's not that many of them, but you can also see on the depth contours how they flatten out and the subduction zone becomes very wide relative to farther south because of that hitting of the delta. So here you can see, again, the subduction zone with some of the recent earthquakes, famous 1762, no known earthquakes onshore, but one of the largest population densities in the world. And one of the things that you see is that as you go to the north, you go from, still for a subduction zone, substantial sediments coming in Sumatra, but that increases as you go along the Bengal fan and into Bangladesh. And by the time you reach Bangladesh, the subduction zone is trying to subduct 16 to 20 kilometers of sediments. And as a result, the accretionary prism broadens out to over 200 kilometers wide. And you can see, I'll show later, all these folds in here of the sediments of the delta essentially coming in and getting folded up. And for comparison, here's that accretionary prism, the active young accretionary prism in Bangladesh and India compared to some of the other ones. And it just completely dwarfs the sizes of most subduction zones. Here's Sumatra, Taiwan, and it's just huge because of the huge amount of sediments coming in. And those sediments continue well into the delta, up past the mouth of the Meghna River. And in fact, you can see in the topography these hills and valleys, which are the sediments being folded up. And these circles show gas wells in Bangladesh, where you can see them lining up and showing that these folds continue blind in the subsurface and also continue farther west in Bangladesh. And I've drawn this deformation front along the outer edge of where these anticlines that have been searched for mainly gas in the subsurface. So in fact, the reason I have to bring up the tectonics is half of the delta is actually involved in the tectonics over here, and the outer part is blind. So here's a close-up of that subduction zone, and it's also the mean topography in here is really flat, and what that implies is that the detachment underneath the megathrust of the subduction zone must be very weak, and in fact, there's a lot of overpressuring. Most big sedimentary basins are overpressured. Most subduction zone megathrusts are overpressured, and now you're taking an overpressured sedimentary basin and subducting it. So here in this box in Silicon, the overpressure is nearly lithostatic. And in fact, mud volcanoes erupted during the 1762 earthquake. So this is the flattest subaccretionary prism in the world. And I divided up into 3 zones. There's the blind fold belt where it's buried, this outer fold belt of ridges, and then it gets steeper and more complicated in the inner fold belt. And so in the outer fold belt, if you look at seismic lines, what you see are these gentle folds. And so these look like detachment folds, like a carpet folding up, that the strata is just being squeezed and is folding up. There's a low velocity zone at the base. And here you can see at the Laomai, the first beginning of that fold beginning to get a thrust fault that's breaking through. And then if you go farther, this is looking farther south, but here you can see some of these folds. And then here's the first one where a thrust breaks through at the, in Teknaf, down at the southeastern Bangladesh, where Cecilia McHugh and Diman Mandal have found uplifted terraces and uplifted corals to look at some of the tectonics and uplift related to the 1762 earthquake. And then once the thrusts come forward, you start seeing more topography. Here at Silicon, you can see these huge sandy turbidites being exposed. There's a Buddhist monastery at the top of this, and you start building the topography, and then you enter India. So Bangladesh is the flat part. Once you get topography, you're in India, and Paul Betker and Nano Sieber have been mapping in the folds that are in the exposed folds, and here you can see one of them where they've mapped it out and worked out the structure of these, which are fault propagation folds. And here you can see, a series of folds that they mapped out, and in the bottom is a movie showing, a hypothetical growth of those folds moving to the west, where you see, fairly simple structures in the beginning. Then you start seeing some of these fold thrust belts intersecting with each other as they grow, and the syncline between disappears, and starting to get more complicated as you move to the west. And this was published by Paul Betka et al. A couple of years ago. And when you put that together with his mapping in the inner belt together, is what you see is this progression of very gentle detachment folds in the front that probably don't take up a lot of strain. Then once the thrusts appear, they're more efficiently able to take up the shortening. The shortening gets more complex. And then finally you hit an out of sequence thrust where that detachment level goes deeper, and you start transferring more of the sediments from the upper plate, from the lower plate to the upper plate. And in fact, you can see in here one of these, shallow thrusts that's now piggybacked on top of these deeper thrusts. So it becomes more complicated as you get to the west. And I mentioned that there was overpressure because this progradation of the delta is going from deeper water, muddy sediments to shallow continental shelf and fluvial sediments that are sandy. What you tend to have is stronger sands on top, and then these muds underneath are overpressured, the fine grained sediments, and that makes a perfect place for the detachment to formulate a weak zone at the base of these sands. And so you can see in this movie of a model that detachment shooting out in front along this weak zone at the base of the sediments. It gives you this very broad, shallow thrust that's incorporating these shallow water to fluvial sediments in the fold belt. Okay, and to look at that in more detail, what I've concentrated on is using GPS. So we've accumulated them starting from 2003 till now. We have over 30 GPS around the country, working with Humayun Akhtar from Dhaka University, and they're split between sort of the stable northwestern part of the country, which is Indian Craton, looking at the tectonics in the east, and looking at the delta in the southwest. And so first I'll talk a little bit about the tectonics, and then I'll move on to the delta, which is the part that you guys are probably most interested in. And most of these GPS we've installed on reinforced concrete buildings. Okay, so here's the kind of data we get from GPS. Here's Nano, Humayun, and I in our field clothes. So the antenna gives you the three-dimensional position of that antenna. And so we break it up into showing the north, east, and vertical components. And you can see that this is Dhaka moving to the north and the east with the Indian plate. And vertically, you can see the subsidence and a very large seasonal component due to the weight of the water during the monsoon. Actually, every summer, the country gets pushed down by 5-6 centimeters and comes back during the winter as the floodwaters recede. Okay, but but because Bangladesh is just the frontal tip of that subduction zone, we've combined with stations, our blue stations in Bangladesh, with stations in red in India and green in Myanmar. And a lot of this work was done with Diman Mandal, trying to work out the velocity. So these are the velocities relative to India, and you can see the overall motion and how it rotates and changes as you go across. And so I just want to quickly cover, we've taken this and broken it up into the shortening component and the strike slip component using a curved framework. And when you do that, you can see this is the strike slip component, and you can see these major strike slip faults like the Sagaing fault and the Chirchampur Mal fault. We now have instrumentation across the Kabah fault, and we can see a strike slip component there as well. And then here's the shortening component that looks very much, you see this broad transition from Indian plate velocity to the Burma platelet velocity, and that corresponds to a locked subduction zone. And what you're seeing is that most of the strike slip is in the hinterland, and most of the shortening component is in the frontal zone. And so the overall very oblique motion is split up between strike slip. The Kabah fault now looks like it's mostly strike slip, and it's your Chirchampur fault, and that leaves you with a component of nearly perpendicular subduction on the order of 15 to 17 millimeters a year. And what that means is because it's locked, there's a huge potential for an earthquake. We estimate it could be at least an 8.2. We're a little bit unsure of where the back end of the subduction of the lock zone is. We currently thinking it's probably in here. And And the frontal zone where those detachment folds are, we don't know if that ruptures in earthquake or not, or if the earthquake would stop over here, or possibly like in Tohoku, most earthquakes only rupture the deep part, but every once in a while you get an earthquake that ruptures all the way to the front, and doesn't make a big difference in the estimated magnitude of the earthquake, but it would make a big difference to Dhaka, which is sitting right by the deformation front, as to whether the earthquake continues to the front or stops at that thrust front transition. And it's very uncertain. It's also uncertain how all the splay faults that go into all these folds, if they would rupture together or apart. And again, does this rupture in one earthquake or multiple earthquakes? How does the recurrence time vary in the tip? And huge amount of uncertainties that where you have a very high hazard, but a bad risk if it happens. And there have been a couple of other papers. So here's one from Malik et al., where he's taken, added some additional data and essentially comes out with a similar story in terms of the shortening and strike slip and partitioning. There's been another paper by Pander et al. From Vineet Kahlal that say that the rigid block of Southeast Asia is the Sunda block, and we should look at the velocity relative to that, and then they get much less shortening. But there is this toroidal flow coming out of Tibet, and that's pushing this area west about an extra 10 millimeters a year. And so the question is, what's the relevant shortening? Is it the shortening relative to the stable Sunda block, or the shortening directly along the profile that you're looking at? And I think, unless this is very superficial, you really need to worry about this, in which case you have a larger shortening and higher hazard. Okay. So, and in order to study that right now, we have an ongoing project involving a large number of groups, where we've put out more GPS, but also we have a seismic line where we deployed in Myanmar and in Bangladesh, 28 and 32 seismometers. And here you can see the teams that put those out. And those are ongoing experiments where we're just beginning to get the results, but I'm not going to talk about it here because that's all tectonics. And so, before I switch to totally sedimentary, I just want to bring up this Shillong Plateau here, where you can see this 2-kilometer high plateau that's in front of the Himalayas. And what this looks like is a forward jump of the Himalayan collision belt, because instead of the Himalayas overthrusting Indian Craton, Shillong can overthrust the thick sediments of the basin, which is easier. And it looks like about a quarter of the motion of the Himalayas has jumped forward to the Shillong Plateau. And when you look at seismic lines in front of that, you can see this foredeep that has formed, that the uplift of the overthrusting of Shillong has pushed down the Sylhet Basin, which is a low swampy area, where my arrow is only about 3 meters elevation above sea level. And this area becomes a big lake every summer that's flooded. And one of the things that uplift of Shillong has done is illustrated here, is that it looks like the Brahmaputra used to flow through northeast India to the sea and was totally separate from the Ganges. But when Shillong was uplifted, it forced a 300-kilometer westward shift of the Himalayas. And now this fold belt has produced the uplift of this old delta. which is exposed now in India. It's just been published in a paper by Ryan Sienkiewicz, where you can see in this section, he goes from pro-delta up to, through distributary mouths and into the fluvial distributary channels through here. Here you can see Nano Sieber taking a look at what we've called the periodic beds. And we think these are the foreset beds of the old Paleo-Brahmaputra Delta. This is only about a third of the exposed section of these varve sediments that we think may be annual deposits of the late Miocene Brahmaputra Delta. If we zoom in a little more into Bangladesh, we can see more evidence of avulsions in the river system, in that if you go back, the Ganges used to flow down what's now the Hooghly River, where Calcutta is, and it avulsed to the east, probably in the 1600s. By the mid 1600s, you could no longer sail from the Indian Ocean up to the Ganges without transferring to a smaller boat. And then in around 1800, the Brahmaputra switched from the old Brahmaputra channel. Here you can see from the first British maps, it avulsed about 100 kilometers west to the Jamuna River. But even in the 19th century, the Ganges and the Brahmaputra had separate river mouths, and those river mouths only combined in the late 1900s. And if you take a look now, what you see is that Meghna River is still widening as a result of that latest avulsion, while the Tutulia channel here that the Ganges used to go through is slowly sedimenting up. So we're seeing, recent avulsions back and forth on the delta. And Ryan Sienkiewicz, who was a student of Steve Goodbread, mapped out some of these fairways and the switches back and forth on an average of about every 1800 years of the river switching from the Jamuna pathway to these other pathways through Sylhet, that the river shifts into here, and then into the Sylhet basin. The sediments fill up the Sylhet basin, and then it jumps back out. And this has been modeled by Meredith Reitz, who you can see pictured here, actually on the Jamuna River. But I want to focus on a smaller avulsion that I've worked on within this system. So if this is a garishly colored topography that from Steve Goodbread, but it nicely illustrates that here you can see the Meghna River and this low elevation basin that floods every year, but you can see this very broad valley that I've blown up here, where there's just a little tiny river flowing through it. And in fact, in this part, the river is flowing northwards, which river should not be flowing north in the Ganges-Brahmaputra Delta. And what we went in with a hypothesis that this may have been a former course of the Meghna River flowing over here that avulsed to the current Meghna River. And so I went out with Celine Graal, joined by M. Winters. And here you can see that, that broad valley, which we went out in October expecting to work on the valley and found a lot of it was still flooded, that it's a little bit lower elevation than every place around, which is why it shows up on the topographic map. Yeah, did some resistivity, went through some of the really terrible roads, drilled some wells, and because Steve had drilled a well in that, and what he found was about 10 meters of muddy deposits over about 30 meters of channel sands. And so we went with the hypothesis that this was an avulsion of that river, and then it's actually down here, this is mislocated, um, drilled 5 wells where we found the transition from muddy channel fill to sandy deposits and sampled at that above and below that contact for OSL dating. You can see the resistivity nicely shows that boundary between the muddy conductive muds and the resistive sands. You can see the channel has a bump in the middle because when you take a look at topography, you can see that there's an island, there's what used to be an island of high ground here, and there's a village on that island, whereas most of this is very low and has nothing but rice fields and brick factories. Yeah, and okay. And another piece is also looking at the physiographic map of Bangladesh that was made by Hugh Brahma, who just died at 95 last week. Very sorry to hear about that. But if we zoom in, what you can see in brown here are all the deposits produced by the Meghna River, both the younger deposit closer to the river and these older old Meghna estuarine floodplain deposits. And within that, he was able to distinguish different soils between this JBA and the JBB of basically a lower elevation. And these are somewhat higher elevation so that they don't flood, and as a result have a distinctly different soil. And if you take a look at that, what you can see is that JBA soil that's related to being formed because of a higher elevation runs right along one of these anticlines. And here you can see the Laumai anticline is the last exposed anticline. And so our hypothesis is that there was an earthquake. We can't tell if it was just a local earthquake on this anticline thrust fault or involved the megathrust, but certainly involved this and produced uplift that blocked this river and caused it to avulse. If you take a look at our OSL dates, what you see is the sediments below. We get 3,600 years, 3,800 years, and we re-drilled Steve's Well 40 kilometers to the north and got 3,800 years, so that what we think is when you project up, we have an avulsion about 3,600 years ago, and then that channel stayed open and then slowly filled in with muddy sediments through time, and it's still not actually completely filled. And then trying to check out some more things, we actually sampled, the only one I talk about, the cut bank of the Meghna River, where this cut bank sample actually also gave an age of about 3,600 years, suggesting that we think the river avulsed, left some deposits in the Meghna that the current Meghna is now eroding into and exposing. So what we see is the formation of the current Meghna River coinciding with the end of this. And so we think we have a large earthquake produced river avulsion that we found here. All right, and so now I'm going to go to completely the southwestern part of the delta to look more at the subsidence. So the relative elevation of the land, depends on, sea level rise, but that also gets exacerbated by subsidence, whether it's natural, anthropogenic, or tectonic, and then is compensated by sedimentation. And I'm working closely with Carol Wilson on the sedimentation part, but I've focused on what's the subsidence, because the subsidence increases the effect of relative sea level while the sedimentation counters it. And in Bangladesh, there's a lot of causes of subsidence. So we have the tectonics in the east producing things, but we also have various compaction and isostasy and various consolidation in the near surface of sediments and fluid withdrawal as well. And in fact, some modeling by Mikhail Kapachev and others suggest that, it's probably the substance is probably about 2/3 sedimentary compaction related and about 1/3 isostasy, with adjusting to that load of sediments. So I want to now look more at the subsidence in Bangladesh and in previous work. So Sally Brown and Bob Nichols published a very comprehensive summary of all the subsidence measurements in Bangladesh a few years ago. But what they got was a huge range of values from uplift to 4 centimeters a year. And part of that is they compiled, all different types of measurements. And if you take a look, you can see that as you go, older records show lower rates. And we're seeing very much the Sadler effect of longer timescales give you shorter times, but you're also seeing huge standard deviations that are as large as the mean value. And some of the things that you have is if you have a well that's picking up deposits, you can get some nice linear subsidence curve. But if a river comes along and avulses in there and excavates a channel and places younger sediments in place, and then perhaps avulses away, if you drill that and get this younger channel sediments, your apparent ages will look like a slower rate and then a very rapid rate that's related to the avulsion. And Celine Grauls called this the channel cut effect. And so you have to be, very careful to look very closely at the context of each of your wells and your dates to try and interpret what the real subsidence rates are. So, Steve Goodbread, as part of a project we had together, has drilled over 400 wells in the Delta using a hand drill technique that he talked about. And he's drilled another 80 or so since then. And Celine Grau looked at those wells with about 200 carbon-14 dates, took into account that channel cut effect and compiled a Holocene scale subsidence. And what you see is that landward of the hinge zone, we see very little subsidence, except where things are tectonic. And we see from the hinge zone increasing subsidence to about 4.5 millimeters a year as you go towards the coast. And these wells will help refine some of those rates near the coast. Included in that, for instance, is a seismic line that we did in 2011 down the Brahmaputra River, where we took a local boat, worked with Volkach Peace and Tillman Schwank, organized with Steve, where we had a little 48 channel, 50-meter seismic data, and the best line was running down the Brahmaputra, the Jamuna River. And here you can see the seismics. This is actually the preliminary processing, but you can see this nice bottom. This is the bottom of the huge glacial valley that was cut during the last low stand. But when you cross the hinge zone, you can see the tilt on that as you see increasing subsidence once you pass the hinge zone. And so that gives us some of the constraint up here. And I just want to add in the tectonic part that I was initially surprised to see that the rates of subsidence in Sylhet were relatively modest, even though we can see a huge downbending of the sedimentary column. And I think that's because of the tectonics, that as the fold belt is advancing blind, it's actually wedging its way in. And so the accretionary prism is actually accommodating a lot of the subsidence. And so the subsidence tapers out here. And it's even more complicated because this is a locked subduction zone. So what happens is now, while the subduction zone is locked, that subduction drags the upper plate down. And then eventually during an earthquake, it will uplift. So that even though this is in the fold belt, and overall, over the long term, it's undergoing uplift, it spends most of its time subsiding. So it will subside, and then we don't know how long, perhaps every 1,000 years, it will jump up by several meters. So it spends most of its time accumulating sediments, but net is an area of uplift. Going to a shorter time scale, we've looked at some historic sites. So this is a picture of Liz Chamberlain next to some salt kilns that were published by Till Hannabooth and Kudras in 2003, and they now have some more sites that they're in the process of dating, and these look to be about 300 years old. Where you build the salt kiln just above spring high tide, and the salt pans are at spring high tide level, and you can see while we're sampling it that it's no longer at spring high tide. The water came up to our knees before we finished sampling, and they get about 4 millimeters a year at the coast there. I've also looked personally at the Shakher temple, which is a temple in the Sundarbans, because Mamin Sarkar looked at 4 sites and got relatively modest subsidence rates. And 2 of these here are in mosques in Bagarat, and I think those are fine. Those agree pretty well with the rates we see. But he has 2 Hindu temples, and the issue at a Hindu temple is that while a mosque is a communal prayer zone where you walk in flat, a Hindu temple is always raised because it's the home of a god or a goddess in this case. So while Mamin put the plinth level, the level that you build up the platform to avoid flooding before you build your building, at the entrance, I think it's at this ridge near the base over here. So we went to this temple, which is pretty hard to get to by boat and hiking through the woods to examine it. And in addition, in a separate trip, Steve Goodbread and Diwan Mandal augured around it and found a brick layer. And if you take a look at if that brick layer represents bricks that are laid down on the base to build up the ground level, they would get about 3.5, millimeters a year. And with that revised plinth level, we also get about the same. And I think, the evidence is that it's about 3.5 millimeters a year. And now, why is there a temple in the middle of the Sundarbans? If you take a look at the old rental map, that temple exists right near where a bunch of the big rivers split into multiple channels. And so that's actually the perfect place to build a fort to protect the river. And so sometime before 1610, the last king of Jashore actually built a fort there, and there's a fort, but it's totally collapsed. And the people who live there also built this temple nearby that is still actually functioning. So now that temple, as the rivers have shifted, is now about 1 kilometer inland from the channel. But I think the better interpretation is that it's about 3.5 millimeters a year of subsidence. And so that actually fits very well with the long-term rates that Celine got. And recently, Melanie Becker has taken groups of tide gauges to look at subsidence rates. I looked at individual ones, and early people looked at individual ones like this one at Kepalpara, and it's, you know, it's not stable, it's bad. But by taking a group of them, they get rid of some of that problem of ones that are subsiding rapidly or slowly and changing rates, and get rates that are very similar to what Celine got. They go up to about 7 millimeters a year. So perhaps a little bit higher in the tide gauges than in the Holocene rates. So here's Celine's map showing increasing about 5, and they show it increasing from about 3 to about 7. So a little bit higher, because this is probably including some compaction closer to the surface. I don't know the depth at which the tide gauges are anchored, but you know, they're anchored, and you're probably getting some young compaction component in it as well, and getting slightly higher rates. Another way we've looked at subsidence is we put together an optical fiber compaction meter. So what we did was we drilled a series of wells and put an optical fiber in. It's the same optical fiber used for communication with these wires. We anchored the bottom with cement and ran the wire, and then we actually have it decoupled from the top. And we had people that would, the family that took care of it would come out once a week and measure the length of the fiber by sending a laser down through it. And we had 6 of these wells at 20, 40, 60, 80, 100, and 300 meters. And then we have a tower from the GPS that, for a GPS as well, that I think was unstable and didn't give us good values. And I have to show you, drilling this well was an amazing thing. We had a team to drill those wells for 2 weeks. This is the rig used for the big ones, where it was rotary drilled, meaning that somebody took a chain wrench, attached it to the drill pipe, and walked in a circle to turn the drill string. But then at the end of it, you have now 1,000 feet of drill pipe in the ground. How do you pull 1,000 feet of drill pipe out of the ground? And this is how they did it. So yeah, they're essentially singing the equivalent of sea shanties to coordinate them. They're actually nonsense words in this case, but they climb up, and after spending 2 weeks walking in a circle, yeah, you can see the drill rig. Since sea shanties have become very popular, I thought I'd show this. So after spending 2 weeks of walking around in a circle and pumping water, in 3 or 4 hours, they pulled the entire drill string out and put in a plastic liner, a PVC liner. Whoops. Yeah. Unfortunately, you know, we set it up next to a river that had filled in and used to be much wider. Here is at high tide, but you can see at low tide it was almost completely dry. And as a result, in 2015, they dredged it. I happened to be there while they were dredging it. And they tried to avoid interfering with it. But, you know, the dredge is very much cuts a U-shaped channel, and then that channel relaxed and broadened, and the system has just fallen into the river and is gone. But here you can see for the 40-meter well, over 5 years that we had measurements, you can see the length of the fiber shortening by on the order of 25 millimeters. And so here is the total shortening of each of those fibers versus depth. And you can fit a nice curve to it that suggests about 9 millimeters a year of shortening of compaction, focused on the top and decreasing, so that below 100 meters we see essentially zero compaction. So we're seeing a lot of very shallow sediment compaction over the over a relatively short time. That's obviously not accommodated in the long-term measurements. And so to look at more detail, we've Steve and I and Carol and others have been part of this project to look at the dynamics in this southwestern area, and that balance of subsidence, sea level rise, river motions, etc., where my component has been focused on the subsidence. And unfortunately, the project was just suspended. But as part of that, we rehabilitated some of the GPS stations that we had installed in the Southwest, and added four new ones in 2019. So we traveled around by boat and car in the latter part, installed GPS. Here you can see my UNAVCO engineer, John Galetska, with one of them. Here I am with one of the boxes that holds the equipment in an abandoned toilet. Here's Carol finishing up installing one of her rod surface elevation tables. So we had people from a number of stations. So, and Bar Orion, a graduate student here, has actually just finished on Wednesday processing the most recent data looking at. So again, here's the one on Polder 32 that was installed back in the fall of 2012. And you can see these rates. And if you fit that, you can get a rate for the north and south. But more importantly, here's a fit of the vertical with this, and you can see the seasonal up and down. But we see about 5 millimeters a year of subsidence at this site. And in conjunction, Carol Wilson, now at LSU, installed rod surface elevation tables. So these are places where they put in a rod down to refusal or 80 feet, and let it stabilize. And then they periodically come back in Bangladesh, typically twice a year before and after the monsoon, and add this arm to measure detailed elevation changes in it. And they combine that with marker horizons to measure sedimentation. So you lay down the marker horizons at ground level and come back and see how much sedimentation there is. At the, after it's installed, this is what it looks like, with basically a cement collar to make sure nothing bumps into it. And then they put this arm on and make the measurements. And of course, because of delays, we had to install it during the monsoon. So here you can see them installing one of these during a rainstorm. And Carol usually had to pound these 80 feet of rods in by hand, which would take an entire day. And this time she bought a gasoline-powered post driver that pounded them in about 2 hours and made things much more efficient. Yeah, so here's in the rain. And we installed one GPS where we put in a rod just like the RSET and then put a GPS antenna on top. We extended it up and this tripod is to support it, but over here it's just a hole so this rod can slide up and down through that. So we have some direct measurements of how does one of their rods actually move, because they're measuring the shallow subsidence, but we don't know that their rod in a place like the Ganges-Brahmaputra Delta is stable. So here's one of their RSETs they installed near Polder 32 a number of years ago in 2014, where you can see they've seen, elevation increases and sediment increases. And if you difference that, you can get an amount of the shallow subsidence. So that now in Southwest Bangladesh, we have a combination of these red circles are 9 continuous GPS installations, including 2 at SNNT, and these triangles are 22 RSETs, where for most of these are in pairs inside and outside of the embankments protecting the areas, or in someplace like Katka or Heron Point in the Sundarbans, closer to the channel and farther away in the natural island interior. And so she has 22 of those, and this is the location of my dearly departed compaction meter. So the advantage of the GPS and RSET is that the RSET measures the surface elevation change and sediment accumulation down to, at most the depth of that rod, and the GPS measures the absolute subsidence. So by combining them, you can separate the shallow component of compaction from the deeper components of subsidence. And unfortunately, COVID has disrupted the measurements of those new sites that we installed. But Masood Rana and Pinky Akhtar were able to go out there in December and make measurements. So Carol now has some measurements that she's just working on to look at, but it's still a very short time series for getting a reliable rate. The reliable rates where there's more repeat measurements, the main one is at Polder 32 that Steve talked about, where it looks like he's getting an 8 to 11 millimeters a year of shallow subsidence. So larger than we're seeing from the GPS. And at Katka is still only a few measurements when repeat measurements, but suggesting similar kinds of numbers, but it's too short to really give you the full estimates. So if you take a look at the subsidence numbers that we have from our older GPS, because we first installed GPS in here, in 2003 and then in 2012, these older sites, the ones in the east, closer to the current river mouth in the sandy areas, are giving, you can see, about 3 millimeters a year, so similar to the long-term rates. And here the historic sites are giving, again, 2 to 4, very similar to the rates that we see from Saline for the Holocene rates. But if you take a look at the stations that we have a bit farther west, you see in the GPS a bit higher rates of, 7, so closer to what the tide gauge is showing, and 5 farther up, suggesting that it's perhaps picking up a little bit more compaction in the shallow surface. These are all GPS on buildings, so they're not capturing the very shallowest subsidence. And yeah, but the compaction meter and the RSET that are getting the shallow subsidence are showing higher rates, around 9 or 10 millimeters a year. And it also just show that I just got back, I just looked at yesterday the newest processing rates, and all I'll say is that our new GPS are giving rates that are comparable, but it's still too short a time to really take those as accurate. You can see the new data has slightly shifted some of the rates, but those may change with time. And so the last piece I want to add in is that we discovered that there are geodetic monuments that look like this. This is one that's been nicely taken care of because it's in the nature preserve, that were and these yellow ones were installed and measured in 2002. So these were installed as geodetic monuments in 2002, measured with GPS, and they've never been revisited and remeasured. So we went out last January in a campaign measurements, and you can see here setting up a campaign monument, a campaign GPS above those, and we measured them from 1 to 5 days. But there are a lot of those. So in this area where we have 9 GPS, we identified 55 monuments, of which we were able to remeasure 48 of them. And, because only 48, because some of them like this is tilted and fallen into the river. We had problems where some of them have a lot of tree cover. We had to use surveyors to connect it to where we could put the GPS in the open field. We had to go through muddy waters, cut down pieces of trees and vegetation. And in the end, we got 48 measurements. These are color coded, but some of them, we have rates that are very low. These red ones are less than 5. The yellows are 10 to 15, but you see these blue ones that are higher than 20 millimeters a year. And we're very worried, are those real? And so here they are without the blue rates, where we see low rates in the Northwest increasing to 10 to 15, mainly in the Southwest. And we did correct for the seasonal subsidence. So if you take a profile through here, what you see is rates over here are low, and then it goes up to higher rates, and then are those real? Because these are not that different from the RSET, but would include deep subsidence as well as the shallow subsidence. And our continuous GPS have much lower rates. To test that out, I was able to send, actually before I say that these rates where they're very low, Steve showed this, that they're along this transect G, where what he sees is much sandier deposits, and closer seaward, we see much muddier deposits. So given that the hinge zone comes near here, and so the total sediment thickness is less, and the deposits are sandier, it's not surprising that we get low rates of subsidence here and higher rates in the muddier parts of the delta. But we revisited, Hasnat went out because with COVID, our instrumentation was left there. So Hasnat was able to go out and remeasure a few sites. And here you can see one of them in the years. There's the 2002 measurement, our January last year, and then here it's remeasured, and you can see you get a nice linear trend on this site. at 14. Here's one of the ones that had a higher rate, and the remeasurement showed uplift. Probably with flooding in this area, this monument is uplifted, suggesting that these high rate monuments are unstable. Because we remeasured 4 sites, the 2 with the moderate subsidence rates came back nicely collinear, and the ones with the higher rates all came out not at all linear. So, I think that suggests that yes, we can throw out these higher rates. We think the monuments may have settled and are now still moving up and down seasonally with motion. And so when you combine all of this, and this is the end of the talk, the GPS on the buildings measures the total subsidence, but relative to the foundation of the building, and so it excludes the shallow subsidence. The RSETs include that shallow subsidence, but don't measure anything below the base of the rods. And the SOB, our survey of Bangladesh monuments that we remeasured and give the highest rate and measure all of it. So combining, it looks like what you're seeing, that there's a substantial amount of consolidation happening in the near surface, that these are picking up, that the buildings are not. And there's several millimeters a year of deep subsidence happening below. There's a combination of deep compaction and isostasy, and somewhat another amount in between. So we're beginning to see a pattern of compaction of subsidence, and compaction decreasing with depth. These numbers don't quite fit with the compaction meter, which suggests that the decay is over a greater distance. And so we still have to reconcile that, but we're beginning to see some of the spatial and temporal and depth variation in subsidence in the delta. And as the RSETs and GPS mature in a few years, we should have a lot more data on this. And so in the future, we want to keep doing that, perhaps look in more detail at the geology at those campaign GPS sites, and continue our measurements. But I think there's potential for getting a lot better understanding of the distribution of subsidence in the delta. And so I'll end there. Thank you.
That's a fantastic, Michael, give this 2-decade field work. That's a fantastic data set of the observation. So in the audience, if you have a question, please go ahead to unmute yourself and ask a question. And because now is almost 10 a.m. So Michael, try to answer your question as short possible, and maybe some. So go ahead. Any question? So when the people get ready, so Michael, I have a quick question. Among all those installations, how many GPS station the data you can see the real data in your office?
Right now, there are, in Bangladesh, we have 15 stations that are online that I can download the data directly. Now, some of those stations we had to, had borrowed receivers and we had to remove them. Yeah. So they're not active. And there's some others that, initially when we put it in, we had to visit the stations each year to collect the data. And so there's still some of those running as well. But in the last few years, we've been putting in cellular modem so we can download the data.
That's great.
Unfortunately, we had a problem with the ones in the Southwest where they forgot to recharge it, and they ran out of money. And so then when they recharged it, somebody had to physically go to each site, pull out the SIM card and put it in a phone and say, yes, I accept the charges, and then put it back in the GPS. And so that only happened in December. So we had a stretch where we, of 6 months where we couldn't get the data. and that only restarted again in December. So we've just been able to, catch up on the processing.
Okay. Great. Okay, so Jim's fast. So you unmute yourself. You have a question, go ahead.
Yeah, thanks, Paul. Hey, thanks, Mike. That was just a fantastic talk. Learned such a lot there. Just ask you one thing. How does groundwater abstraction affect subsidence in some areas? I was just wondering what the relative sort of magnitude of that might be.
The main place where we see that is in Dhaka, where our GPS in Dhaka are showing 11 to 12 millimeters a year of subsidence. So these are, again, ones on buildings where, elsewhere we're seeing, at most 7 in the highly subsiding areas. In Dhaka, we're seeing 11, 12 millimeters a year where, where there also isn't any sedimentation going on.
Yep.
To drive some. So we think, I say that probably 90% of that is from the groundwater extraction.
Okay, thanks.
Yeah, and so we have several campaign monuments set up in the center and going out away from Dhaka to look at that, how that subsidence varies with the cone of withdrawal, because
Right.
the water table under Dhaka is below 70 meters now.
Okay. And also one other question just about those differential rates you were showing at the end, where you got the very high rates that you think that, the monuments may be unstable. Can I ask you, in terms of the what's in the substrate and variability locally in terms of, percentage sand, clay, can that have any effect on that?
It definitely can. And so, I try to look from, what I could to see about that. And, certainly some of those unstable ones were like that, whereas on like the side of a road that, was built up and, may not be stable. But that's one thing when all this ends, I'd like to go out there and, perhaps with Carol and do like auger holes around a lot of these monuments, particularly these unstable ones, versus, or do a mixture of them to see what's going on.
Right.
And what the lithology looks like. I've looked at some of Steve's wells, but most of them are not within 3 or 4 kilometers of these wells, and so there's a lot of variability as to what locally may be going on.
Okay, and many thanks. It's just amazing. There's so many of those around. It's incredible. Hey, thanks, Mike. That was really enjoyable.
Yeah, no, it's amazing, and there's ones all over Bangladesh. Unfortunately, the ones in the northern half of the country, they can't find the original GPS data. But in the southern half of the country, we have the original GPS data from 2002 that we can reprocess.
Okay.
Thanks, Mike.
Nice. Anybody else? If you have a question, please unmute yourself. Just go ahead.
Yeah, maybe I'll stop sharing so I can see all of you.
So, Michael, with the question, could you answer briefly on this 20 years field work and the data accumulation? What did we learn from Ganges-Brahmaputra and the lessons, how we can apply these lessons for other world major delta system, like Irrawaddy, like Mekong, like Yangtze, even Mississippi River Delta?
Yeah, as you know, in the Ganges-Brahmaputra right now, the sediment in many ways is the subsidence rates, if you exclude the very shallow rates, the deeper rates are probably lower than a lot of delta. A lot of the big deltas like the Mississippi and the Niger and the Nile are sort of collapsing seaward under their own weight and adding to the subsidence. In Bangladesh, what I think is happening is that the Bengal fan has so much sediment that the continental rise goes up to about a kilometer elevation, a kilometer and a half, and that's higher than the top of overpressure. So it's effectively acting like a buttress,
Mm.
so that the delta is not sliding seaward the way other deltas are. So the subsidence is somewhat less, and they still have sediments coming in. You know, I didn't talk about the sedimentation, but the measurements of sedimentation rates, you know, are showing, you know, an average of a centimeter a year of accumulation in places. So it looks like the sedimentation is keeping up with the subsidence overall. That
Okay.
and that's not true in a lot of other deltas.
That's right.
We're very concerned about future plans for river diversions and dams that might cut off the sediment.
Sure. Definitely.
In fact, where the biggest problems with subsidence are is actually inland, where humans have intervened and built embankments and stopped the natural flow of sediments.
That's interesting. Looks like your GPS installation maybe marked the most, how to say, that the number on the delta. If you think about the rest of the world, the major delta, the Nile River, the Mekong, even the Mississippi, I don't think there's so many GPS installed over the delta. Is that right?
No, I don't think, you know, I don't know. I mean, there are some. I don't think as many.
As many as what you did.
As what we have.
That's
and
great.
I think what will be really important, you know, in a few years is that combination of the RSETs and GPS together, because we've you know, we now have these, you know, 9 locations where we have them within, you know, a few hundred meters of each other.
That's fantastic. Other question, you see a very good seasonally variation, the change. So that could be because of water sediment. But did you see any signal when the big storm coming made a landfall? Is there any that kind of spark or caused us, you know, subsiding or suddenly rise?
Look, I mean, the GPS, we're averaging each, you know, daily amounts. So, well, actually, yeah, we do. When we've modeled this in our paper, you can see, you know, some of the shorter term scatter in the GPS. You can see is you know, storm and flood events that are showing up in the GPS data.
That will be, you know, when we get a 5 or 6 meter storm surge, I'm pretty sure there should be something we can clearly, you know.
I mean, I haven't looked for like cyclone storm surges, but in our 2010 paper, we modeled this, you know, where we took water level data from the Bangladesh Water Development Board and took that as a load on an elastic plate and calculated the deflection, and were able to fit the GPS data really well.
Good.
And now we have more groundwater data and more GPS, and we're hoping to advance that again.
Okay, that's very nice. So from the audience, anybody have any other question, any comments, anything? And
quite little bit different from a lot of the sedimentation in other talks.
Well, that's the exact, but what we need this observation, and this is definitely a very good source to think topic. And if not, I will say now, you know, we know it's already 10 and 20 in the East Coast. So I would like to see next Wednesday, we have a great talk, you know, from our colleague in Poland, So the source to think in the high latitude, particularly sedimentary accumulation and organic carbon in a void. So, and also next Friday, Charlie Paul, he will talk about the Monterey Canyon observation all the way the sediment transport to the deep sea. And so please mark your calendar and coming back next week. And so if you know any other question, I would thank you, Mike, very much. Thank you all the audience and attending this series. And so I hope you have a very good day and